Okay, so revision, second revision lecture, chapter 6 to 10. So last week we finished off with the first chapter that dealt with multiple degrees of freedom, okay, chapter 5, and chapter 6 was a continuation of that to look at forced multiple degrees of freedom systems, okay, and that involved using this thing called the modal analysis technique, or modal analysis, where you basically instead of trying to solve simultaneous differential equations, you can separate it out into equations that represent the modes of the vibration, and then you can convert it back to displacements. The first three steps are from chapter 5. Okay, you've got to find the equation of motion in matrix form. From that, you can work out the mechanical impedance matrix, and you take the determinant of that, and you can get your natural frequencies. Okay. Step 3 was to find the mode shapes. So you take those natural frequencies, you insert them back into the mechanical impedance matrix, and you calculate the mode shapes. So those three steps, like I said, they're all from chapter 5, and they should all be revisioned for you as well, because that's from level 2 dynamics. But the new stuff starts in step 4. Okay, the first thing you need to find is the modal mass, or modal masses. Okay, so for each mode shape, the equation is here. You take the transpose of the mode shape, multiply it by the mass matrix from your equation of motion, and then multiply it by the mode shape again. Okay, and that will give you a value, mi, which is the modal mass. Okay, and you do that for each of the mode shapes that you've got. So if you've got, say, a 3 degree of freedom system, you'll have to do that 3 times to get 3 mi values. Okay, then what you need to do is you need to rescale those mode shapes. Okay, so you've got the mode shapes to what's known as unit modal mass. So you take your mode shape, so that's those 3 values in a row, in a vector, and you divide it, each value, by the square root of your modal mass that you found in step 4. Okay, well that will give you a new vector, okay, of say 3 values or 2 values, which we call u. And then you line up all those vectors, u1, u2, u3, and so on, and that will give you what's known as the modal matrix. Okay. We'll do an example of this so you can see what we're talking about. You then have to deal with the applied force. Okay, so that's big QI is the force, the modal force. And what you do is you take your modal matrix, which is phi, you transpose it, and then you multiply it by the forces that were given in the question. Okay, they may be linearly increasing forces, they may be sinusoidal forces, you don't know, but whatever they are, you multiply them by the transpose of the modal matrix to give you your modal forces. Once you've got big Q, you can then stick them into your equation. Okay, your equation will always be in this form. This is the case with damping. If there's no damping, obviously zeta is 0, so that middle term has disappeared. Okay, but it'll always be in that form because you've rescaled the unit modal mass, so that the coefficient for Q double dot is 1. Okay, and you'll end up with omega I squared in front of the Qi term over here. You rescale to the unit modal mass, that's what you'll get. And like I said, if there's damping, you'll have this term in the middle. And if there's no damping, that term will be 0, so it will have gone. And this is quite nice. This is an equation that we know how to solve. Okay, we did that back in chapter 3. Instead of q's, we had x's, and we had mx double dot plus cx dot plus kx equals some forcing function. Okay, and your equation will match that up very nicely. Okay, the equation you've got here. And so you can use the solutions we found in chapter 3 to find the solution to that. It's simple mathematics. Essentially, chapter 3, although we were solving vibrational problems, we were solving differential equations. Okay, and we came up with a solution for that differential equation. Well, it just so happens that that differential equation matches up the differential equations we were solving in chapter 3, so you can use the solution in the same way. And then once you've got a value for Q, you'll find a Q as a function of time. You then multiply that by the modal matrix, which is this key, and you get your displacements back. Like I said, one of the examples that I'll do today will be using this method to sort of revise for you this method that we did before Christmas. So that's chapter 6. Chapter 7 introduces the idea for nonlinear systems, okay? And to solve for nonlinear systems, we often use the energy methods, okay? And in particular, Lagrange's equation, which we'll see on the next slide. But there's a 5-step process for this method, okay? The first step is you have to take a look at the system, and for the whole system in general, okay, you need to find the kinetic energy. So if things are moving, whether they're rotating or moving left and right and stuff, you have to find the kinetic energy of the system. So obviously 1/2 mv squared if something's translating in a linear fashion. You've also got to find the potential energy, V, okay, and the V will be the gravitational potential energy, so mgh, or it'll be a potential energy contained in a spring, so 1/2 kx squared. Okay, and sometimes it will be both of those things, and again we might do an example with that today, where you've got only a spring and a pendulum, okay, and the spring and the pendulum both have potential energy. One obviously is the spring potential energy, the other is the gravitational potential energy. We'll do that. If there's damping in the system, then you have this term R as well, okay, R being Raleigh's dissipation function, and that is 1/2 c, which is the damping constant, times your x dot squared, so your velocity squared. And then you compute L, and L is simply the kinetic minus the potential energy. Gives you this equation called the Lagrangian. That's step 1. Step 2 is you have to take the differential of L with respect to the velocity of the variables you're interested in. Okay, I've just called them Q here, just for general coordinates. Okay, but say you've got x1 and x2, because you've got two translating masses, then Qi, or Q1, would be x1. And so you have to take dl over dx dot 1 to get the first term. And then you take the time derivative of that to get the first term in the Lagrange's equation. Okay, so you've got this term. Okay, you then take the derivative with respect to time for the first term. You then have to compute dl over dx. Okay, so there's no dot here now. So you, like I said, it'd be worthwhile you revising your differential rules or differentiation abilities to solve these sort of questions. And then the next step is to take R and then take the derivative with respect to x dot, okay, or q dot. And once you've got those three terms, so this term, and this term, you can then plug them into Lagrange's equation, which is on the next slide, and you'll get the equation of motion for each of those variables that you're interested in. Is that a question? No. And there's Lagrange's equation. So you say there's the first term, you subtract the second term, and you add the third term, and then there's your force at the end, okay? If you've got a force being applied. Obviously, if there's no force being applied, then Q, big Q, at the end is 0. And that's your equation of motion for a nonlinear system. So, you know, for linear systems, we looked at, you know, where you laid it out in a matrix form, okay, and we had torsional systems and we had translational systems, systems with springs and masses that move in a linear fashion. You can obviously very simply go from the drawing to a matrix form of the equation of motion, and we showed that in when we covered this stuff that it works, okay. But obviously the advantage of this is if there's non-linear elements to that system. So say you've got a pendulum. Pendulum is a non-linear system, okay. If you don't assume small angles, it's a non-linear system. And so with a simple pendulum, you apply the same thing and you get a non-linear equation, okay. It's much more difficult when you've got if you're trying to do it using first principles. So that's nonlinear systems. That's the end of book 1. Book 2, we spent a few weeks looking at Fourier transforms. Okay, and Fourier transform is simply a way to represent a function, okay, a function in the frequency domain, okay, represent a function as a frequency spectrum. Now we actually did Fourier transforms back in chapter 4 when we were looking at Fourier series, okay. If you plotted along the x-axis all the different frequencies, okay, so omega, 2 omega, 3 omega, and so on, okay, and you plotted up the y-axis your value for an and bn, you had a bunch of lines, okay, all those values, that was a frequency spectrum representation of a periodic signal. Now Fourier transform can extend that, because what you can do is you can look at non-periodic functions. Essentially a function where you assume it's a periodic function, but you assume the period between each instance of that function is approaching infinity. So you end up with a continuous line in the frequency spectrum. Now the equations for doing a Fourier transform, simply you take the function in time and you multiply it by e to the minus j omega t, you integrate it and you get your f omega. Okay? And then you can do the inverse Fourier transform, f minus 1 is a very similar equation. You've got 1 over 2 pi out front, and instead of e to the minus j omega t, you've got e to the j omega t. And this is your frequency domain function, not your time domain function. Okay, so you can go from one to the other. And if you know f of t, and you can integrate analytically, then you can find it. We did that. We did that for a exponentially decaying force, and we also did that for a rectangular force, a box. Okay, and you can look up in the notes the methods behind that. But what's really useful is to know the pairs. So for example, with the box function in the time domain, you know you're going to get this thing here is going to be a sinc function. Okay, and if you've got a sinc function in the time domain, you take the Fourier transform of that, you're going to get another box. Okay, and so on. There are some properties to be aware of. Linearity. Okay, if you've got the Fourier transform of two functions added together, that's the same thing as taking the Fourier transform of one and adding on the Fourier transform of the other one. The other point you can make is if you multiply a function by a constant, you take the Fourier transform of the function and then multiply it by the constant, you get the same thing. Okay? Linearity. Shift properties. If you shift something in one domain, it involves a multiplication by a complex exponential in the other domain. So here we've got a time shift property. So you've got some function in time. If t naught is 0, then it's centered upon t equals 0. Okay? But if you shift it by a certain amount of time in the time domain, then you take the Fourier transform as if it hadn't been shifted, and you multiply it by e to the power of minus j omega t naught, where t naught is the time that you shifted it. Again, the notes have examples of this. Frequency shift is similar. Okay, if you've got something in the frequency domain that's been shifted over by a certain amount of omega naught, okay, so you've got, say, your sinc function, it's shifted over by omega naught, then the inverse Fourier transform of that will be your Fourier transform as if it hadn't been shifted, multiplied by e to the j omega naught t. Okay, where omega naught is the amount you've shifted in the frequency domain. So, like I said, in other words, shifting a function in one domain corresponds to a multiplication by complex exponential, so that's e to the j omega naught t, or e to the minus j omega t naught function in the other domain. Okay, that's the shift properties. We also talked about delta functions, because that was introduced the idea of an impulse. Okay, and then that led on to talking about convolution. Now, when you've got a system, okay, mass spring damper system or any sort of system, you give it an impulse input. Okay, it'll respond, and that response is known as an impulse response. Okay, makes sense. It's a response to an impulse as your input. Okay, and that system will always exhibit that sort of certain response. Okay, and what you can do is, if you take your forcing function and you break it up into a bunch of impulses, okay, each of those impulses will give an impulse response of a certain amplitude and at a certain time. You can add up those responses, you get a solution. Okay, and what you can do convolution allows us to take the forcing function and you convolve it with the impulse response and you get that solution. Okay, instead of having to break it up and then solve for each of them and add them up, you can just convolve it. Okay, which is what the convolution does. And essentially, convolution, where's the picture? So here, for example, this is an impulse response, a critically damped system. Okay, you give it an impulse, that's what it's going to do. Let's say our forcing function is a box, okay, in time. Well, what you do is you take your impulse response, you flip it over, move it over here, and then slide it over the box, okay, and you take the integral of that, and the integral of that will give you a value, okay, and the values will change as the box slides across the top of it, and there's your response, okay. So our system, a critically damped system, if you give it a kick, we'll do that, okay? If you give it an input of a certain value, here value 1 for 1 second, then the response is going to look like that, okay? Which makes sense. So like I said, you take the impulse response, you flip it over, you move it over here, and you just slide it along the time domain, and you take the integral of the intersecting areas, okay? And you get your response over there. So that was chapter 8. It took a bit less time to revise that than it did to actually cover it. But that's essentially what you need to remember from it. Chapter 9, digitisation. This was a sort of a light reprieve following chapter 8 and all the maths in chapter 8, because this is much more, I guess, descriptive and qualitative. Essentially, digitisation, if you're conducting computer-based analysis on a system, okay, you need to convert the signals, the analog signals, into digital signals for the computer to be able to work with them. Okay, and there's a two-step process. The first step is to sample and hold, which essentially quantizes the time domain into certain sample numbers, and then you convert the analog signal to a digital signal. So depending on the resolution of your digital converter, okay, you get a certain integer value for each of those values of your analog signal. Okay, so there's two steps: sample and hold, and ADC, and analog to digital converter. And that, like I said, quantizes the time into samples and values into digital numbers. And both of those things, samples and digital numbers, are going to be integers. Okay, so you're basically, although what happens between two sample numbers is immaterial, okay, because it's only taken the snapshot of one sample, and then it waits a certain amount of time, depending on how frequently you're taking values. You take a snapshot at that point, you take a snapshot at the next point. What happens between doesn't really matter. So that's the sampling bit. And then for each of those values that it's picked at those 2 points, it needs to find a value on the digital scale, okay, a particular value that it's closest to, okay, and that's the ADC bit. Again, that will be fixed at a certain integer value. Between integers, it can't really deal with, so it'll move it to one or the other. An issue that you've got to watch out for is aliasing, okay? And that aliasing will occur, or can happen, if your sampling rate is less than 2 times the frequencies you're interested in capturing, okay? If it is less, you might end up with aliasing, and we saw an example of aliasing with a helicopter being videoed. It looks like the blades aren't turning. That's an example of aliasing. Obviously they are turning. And like if you ever see videos of wheels on a car or something, they look like they're going backwards. Well, they're not going backwards, it's just that the frame rate of the video is obviously not twice the frame rate of the rotational speed of the wheel. So aliasing is something to watch out for. And then, back in chapter 8, we talked about Fourier transforms. Well, you can apply Fourier transforms to digital signals. It's called the discrete Fourier transform. And one form of that, the most efficient form, is called the fast Fourier transform. And that can be used to extract frequency information from time domain signals in the digital signals. Okay, it's just so that you're aware that Fourier transforms apply to that as well. Okay. And we saw an example, Sam, when he was doing his presentation about the testing. Okay, he showed you a frequency domain signal that he took from when he was testing the response of a rig that he was giving vibrational tests to. Chapter 10 introduced random vibration. Okay, so random vibration is also known as non-deterministic vibration, because basically, deterministic means we know the displacement, and from the displacement and the time we can work out the velocity, and from the velocity and the time we can work out acceleration. So you know everything about it, you can determine everything about it. Random vibration, you can't do so, okay? It's random, that's the whole idea. So the details are unknown, but the statistical information is known. Okay, so you can work out things like the mean value, okay? You can work out the mean square, and you can work out the standard deviation, or the variance, okay? There are relationships between all of those. Again, look in the notes and you'll work them out. And you have a probability density function, and that's px, okay? Probability density function, or PDF, is essentially a function, and your values of your random vibration will occur underneath that function somewhere. Okay, so the integral of that px term will be 1. There's 100% chance that your value will appear underneath that function at some point. Okay, and the px can be any sort of shape. And what you can do is by changing the limits from minus infinity to infinity to be, say, between 0 and 2 or whatever, you can find the probability that your value between 0 and 2 will be in that function. And obviously that will be less than 1, so you give you a percentage. We talked about that back in the beginning of chapter 10. Now the important information that we want to work out is what's known as the root mean square. Okay, the root mean square, or the square root of the mean square, so it's the square root of ex squared, is known as the root mean square, which is the statistical measure of the magnitude of a varying quantity. And the examples that we looked at, the idea was to find x RMS. How do we find that? Well, we talked about power spectral density. And power spectral density is a Fourier transform. Okay, it's a frequency domain signal, okay, that shows the strength of the variations as a function of frequency. Okay, it's a Fourier transform. And we're often talking about, in vibrations, we're actually talking about sort of acceleration power in inverted commas. And the process that you had to go through, first off you had to find h omega, which is a complex frequency response function. Okay, and it's essentially a transfer function. For those of you that did control systems, you'll be probably sick to death of transfer functions, but essentially it's a transfer function between the input and the output, okay, in the complex frequency domain. And that transfer, that relationship between input and output also applies to the spectral density of the input and the output. Okay, and the relationship is given here, where you could take the magnitude h omega squared, okay, times by the input will give you the output. And if you take the integral of the output, power spectral density, you get the mean square. And obviously you take the square root of the mean square, you get the RMS. Okay. So the problems we looked at were things like road surfaces, okay, where you have a spectral density of the input. Okay, you multiply it by the h omega magnitude squared. Okay, you integrated and you've got your RMS value for the for that particular road surface. And that's chapter 10. So that's a very brief overview of the rest of the course.